Okay, so hey everybody, I'm just gonna go ahead and pick up where I left off with these problems, with the ones I didn't get to during the review. I'm gonna post this video probably either on YouTube or upload a link to Google Drive for you guys to watch me solve the problems. But I'm just gonna go through the ones from chapter 1 and 2 that we didn't get to, and if you have any other questions, as always, feel free to reach out. Um, so this first problem here about shadows says there's a screen 40 centimeters to the right of a point source, and the shadow is formed by a dark disk with a radius of 2 centimeters. That disk is 30 centimeters away from the screen, and the question wants to know what is the diameter of the shadow formed by the disk, and what is the name for this type of shadow. So starting out my drawing, I'm going to um, go ahead and draw my point source, which is going to be just light 40 centimeters to the right of a screen. I'm sorry, to the left of the screen's to the right of the point source. I'm going to draw that here, and I'm just going to draw some rays kind of coming off of it here, that where they would go for now. Oops. Something like this. And then it says the disk is 30 centimeters from the screen, so we'll draw our disk here. And this distance is 30 centimeters, and this distance is 40 centimeters. Okay. And then it says there's a shadow formed on the screen as well. So we're just going to assume this wavy line is our shadow being formed here. And the radius of our disk is 2 centimeters. So that means the total length of the disk is 4 centimeters. Okay, so using this information, we're just going to use a proportion. This type of problem calls for the use of similar triangles, which is just a fancy way to say proportions. So I'm going to compare the distance from the point source to the shadow as one large triangle. So as one of our pieces of the proportion. So this triangle here, we're going to compare to figure out how big the shadow is. We want to compare this, like this unit, or this, like this measurement, and this measurement. Okay, so we know that we have 40 centimeters and our unknown value, and we can compare that to our other triangle here, and we can do the same thing. We can compare this value to this value. So our distance portion of that triangle is going to be 10 centimeters, because it's only this much of the length from the light to the screen. And then we know that the diameter of that is 4 centimeters. Okay, so when you solve out for the unknown variable, you get 16 centimeters, I believe. So that's not right. You guys can check my math on me, but that's what I have written down here. So we're going to go with that. So that's that problem. The next problems we were talking about were similar, but this is about depth of field and focus, where we're still going to be using triangles for the most part to do our problems, but which is like a little bit of added concept. So we're going to draw after I read the problem here. So it says, someone is modeling for a magazine cover. Someone else is taking the photos with a pinhole camera. The film plane is 3 centimeters from the aperture, and the model is standing 3 meters from the camera. Okay, so if the model is this tall, which we'll convert that to centimeters, how tall is the image on the film plane? And then include value sign in units. So that's important to remember, because for these heights, for this kind of problem requires a value slash, well, no, it requires a sign. Obviously has a value, but the sign is going to be positive or negative because we know that pinhole cameras create a negative slash inverted image, okay? So first things first, I'm just going to tell you guys the conversion for this is 73 inches, which is about 185 centimeters or so. And then drawing out my stuff here, I'm going to draw the person, and they are, we're going to say 300 centimeters because they're 3 meters from our camera. We're going to call this our camera. And this is our pinhole. That's where the light is going to go through. And then there's a screen behind it. So let me change the color, I guess. So, and then there's a 3 centimeter, this is obviously not drawn to scale, but here's our 3 centimeter distance away, the film plane where the image ends up, okay? So for this, it's like the exact same thing basically, where you're gonna, as the last problem, where you're just gonna be using triangles to determine how tall the shadow is, or I'm sorry, the image that's created. So if we draw, we know that a pinhole camera has one ray for 1 point source. So we're going to draw one from the head, and then we'll just draw one from the foot as well. Something like this, which that's not really drawn to scale either. I'd rather this crossing be over here somewhere, but it's fine. Basically, well, actually, you know, to be honest, the crossing has to be at least like more. See if I can do something like this. This isn't going to look as good. I'll just change them. Oops, no wait, I want to move this. Nope, not that too, oh my gosh. I'll just move it like this. There we go. So there, we'll draw it like that. That way we have better triangles to work with. So for this first one, we know the height of our person, which we're going to compare that to the height of our shadow, which we don't know. I'm sorry, our image, which is this height. We're going to compare it to this height. So that's one part of our triangle. And then we're going to use this distance and this distance as the other part of our proportion. So 300 centimeters here. And if you guys are using signs, which you should be, I guess, for the distances here, we know that I'm an upright thing. So we're an upright, or the model is an upright entity. And then the distance is going to be negative because we're measuring away from this point source, I want to say. Yeah. Let's see. No, wait, this is the flow of light is this way towards this source, and we are measuring from the wavefront to this source. Well, no, that's wrong because that's with the flow of light, and this has to be negative. So we're measuring from this point back to this point source, and that's negative. Okay. That was probably confusing. Sorry, let me erase this and tell you again. So the negative 300 centimeters is the distance from, we're just going to say like this point here backwards to our point source. And since we're measuring this length here, which is 300 centimeters, we're measuring from here basically to this source, okay, which is the point source on the head or wherever. And that's going to give us a negative 300 centimeters for this part of the proportion. Vice versa, this is going to be a positive 3 centimeters because we're measuring from this source. I'm sorry, we're measuring from this point here backwards. No, oh my gosh, I'm confusing myself. We're measuring from this wavefront to this point. Okay, just the exact same as the other one. I don't know why I messed it up in my head there, but we're measuring from this point back to here, which is with the flow of light, which is positive direction, okay? So you don't really need to remember all that complicated information as long as you remember the fact that at the end, your image height should be negative because a pinhole creates an inverted image, okay? So that's like the main concept there. Once you solve out this proportion, you get something close to negative 1.85 centimeters or something like that for the height of the image on the film plane. The next question is conceptual. So if the cameraman wants a photo with a blurred foreground and background while maintaining clarity of the model, should he use a large or small aperture setting on the camera? Well, and what if he wants everything in focus? Well, we know that if he wants everything in focus, he should use a pinhole camera because that's what he's kind of doing right now. And we know that for a pinhole, the depth of field and depth of focus are theoretically infinite, which means that everything is going to be clear all the time, no matter where you move it, if you're using a pinhole camera. So in that case, you can't have smaller than a pinhole. So if he wants to have a blurred foreground and blurred background, then you would have to use a larger aperture. Okay. So I'm going to move on to the other problem that I skipped somewhere. Okay, so this one is about the question that we were talking about, which we kind of talked about during the review, but I'm just going to draw it out for you guys. And you guys can also like plug in your own numbers if you wish to prove this, like to do a proof. But basically, does red or blue light have a larger critical angle? So what we're talking about is the critical angle is the incident angle going from an index of high refraction to a low index of refraction. And that angle produces an emergent angle of 90 degrees, okay? So perpendicular to the normal. We already know that blue light is going to be refracted more as it passes through a different medium, and red light is going to be refracted less because of wavelength. So shorter wavelength light is refracted more, and longer wavelength light is refracted less. So if you think about it conceptually right off the bat, you can say, well, I know that the blue light is going to be refracted more. So we also have to understand the concept that the larger the incident angle, the larger the emergent angle. So if they're both going to end up being bent to 90 degrees as the emergent angle, they're both going to end up 90. Blue light is going to be bent more. So it needs it can use a smaller starting angle to end up getting to 90 because it's going to be bent more due to the properties of refraction. Red light is going to need a larger incident angle because it's going to be bent less. So in order to get to 90 as well, you have to put more work in. The system has to put more work in to get the red light to bend as much as the blue light. All right, so that's why it has to start. Red light has to start out with a larger critical angle, or with a larger incident angle, which is the answer that red light has a larger critical angle than blue light. If you're curious and you want to try to just do the math for it to solve for critical angle, you can just use random values, because we can say that for the same index or for the same material, the index of refraction, we know it's going to be less for red light. So we can just say the index of refraction for the red light for the same material can be 1.5. And for the blue light, we can say it can be 1.6 because we know it's going to be a little bit higher, which 1.5 to 1.6 is an exaggeration. Typically the differences for wavelengths for index of refraction for the same material are like a much smaller difference, but still different. And then if you solve these, for this one, you get the critical angle would equal 41.8 degrees. And then for the blue one, you get the critical angle equals 38.7. So you can see that the blue light would have a smaller critical angle and the red light would have a larger critical angle. And this is assuming that they're, going through the same system. So from water to air, for example. We use a different index, of course, but that's just theoretical. So that's that concept. Let's look and see if I had any other ones. Okay, this one here is talking about lateral displacement, which a relatively simple problem. So a monochromatic ray is incident at 30 degrees on a 20 centimeter thick polycarbonate block surrounded by air, and its index of refraction is 1.59. What is the lateral displacement between the incident and emergent rays? Okay, so basically we're going to be using our formula here, which is D equals thickness times the sine of theta 1 minus theta 1 prime all over the cosine of theta 1 prime, okay? And then once we find our values, we're just going to plug all the stuff into the equation and get going. So what do we have so far? Well, we know we don't have the lateral displacement yet because that's not given to us. We know that our thickness is 20 centimeters. Make sure you change this to meters. That's important for the equation. It won't work unless you use everything in meters. Sine of our theta 1, which we know is 30 degrees. We're not given theta 1 prime yet, so I'm going to just leave that blank for now. And then we can't do the other part either, so I'm going to leave that blank for now too. So I'm just going to go ahead and draw a picture for you guys just to get an idea what it's going to look like. So this question involves Snell's law, as well as understanding parallel-sided elements. So we're going to say that we have an incident light here of 30 degrees to the normal. Let me draw on our normals. We can just say that this is a normal up here too, because I'm going to draw the refracted ray out that way. This is 30 degrees, all right? Our light is going to bend through this somehow. That doesn't look like very bent, but there, that bends it. And then it comes out like this, something like that. We're not going to solve for this really, but no, I lied. I don't want that one. I wanted to say something. I want to look like this. There we go. And we can see that if this red light had continued through, it would have came out like this, but it didn't. So what we're going to do now is measure, what the formula is measuring is this distance here. It's not a 3, but I can't draw one of those little fancy shapes, but that basically, which also looks bad. So let's do this. Okay. So that's what the setup is going to look like. We know that our index of refraction of this block is 1.59, and we know it's 20 centimeters thick. We know that we're assuming that we're in air out here, so we're going to use that for that part of the Snell's law. And we're just going to do n sine theta, not theta prime, equals n prime sine theta prime. Okay, and that's going to that's what we're going to use to figure out what theta prime is. When you plug the values in, you're going to put 1 here, you're going to put 30 here, we're going to put 1.59 here, and then we're going to solve for this variable. You end up getting 18.3 degrees, and that is the internal angle here inside of the plastic. So now that we know that theta 1 prime is 18.3, we can just plug it in up here. And then for displacement, it comes out to be 4.26 centimeters. Most likely when you first solve this on your calculator, it's going to be put out into meters. On exams, you can type it in as meters, or you can just convert it and type it in as centimeters, because more than likely it'll be a free response question. And you will be able to type in whatever units you want unless she specifies otherwise. She might put, please put it in centimeters, please put it in meters. So just make sure you pay attention to see what she's asking for. That's that problem. And we didn't do apparent position, but it's not going to be on your first exam, so we'll get to that later in future reviews. And that's it for the first 2 chapters.